Okay, today we're going to continue our discussion of quantum mechanics by talking about the implications and the applications of things in quantum mechanics. And this is our Friday class. And I start off the Friday class with a little quantum poem here. And so we think about the little quantum poem. But I also start off Fridays. They're Freddy Fridays. A song for talking about quantum mechanics because it makes the notions of reality. I show a picture of Freddie Mercury and I play some Queen music. Is this the real life? Is this just fantasy? Caught in a landslide, no escape from reality. And appropriate, however, more fuzzy. That's our Free Friday. And we're going to talk about quantum mechanics implications and applications. But before I do that, I want to remind you, when you're doing problems, concepts first, equations second. So here was one of the problems on the homework assignment. If you trap this gas of atoms, you want to calculate the de Broglie wavelength. I want you to remember this has to do with, as you slow the atoms down, it changes their wavelength because it's the de Broglie wavelength thing. You do not use this relationship here. This relationship has absolutely nothing. And so what some of you did, you little scamps, you said, oh, I am given a temperature and I want to find a wavelength. I'm going to find an equation that relates wavelength and temperatures. I'm going to use that to calculate. Oh, no, no, no. This, if you did this, this makes Brian very, very sad. This makes Brian sad. I'm even going to make a little tear. Here's a little tear coming out of mine. It makes me cry. Because what you're doing is you're just taking numbers and sticking them into equations. You don't want to do that. You don't want to do that. What you want to do is think about the concepts. As I cool atoms down, I'm changing their speed, and so I'm changing their de Broglie wavelength. That's what this equation is about. A problem that has nothing to do with this. So if you started doing this, you scamp, go back and finish that and do it the right way. Now, I want to do a quick warm-up, and I want to use some of the concepts which we used previously, and I want to connect it to the quantum mechanics stuff we're doing right now. So silicon solar cells behave like batteries, and they have a 0.5 volt terminal voltage, okay? So here's your question. Suppose 1 watt of light of wavelength 600 nanometers falls on the solar cell, and 50% of the photons give their energy to charge carriers, creating a current. What is the solar cell's efficiency? That is, what percentage of the energy incident on the cell is converted to electric energy? Okay? This was a past exam problem. In this one, before you dig in, I want to take a little bit of time to kind of like sketch through how you would think about this. But this is a really, really substantive problem that connects together everything that we've done. This is the kind of thing I have asked on exams in the past, on an exam. So take the time. So I want to look at the steps in turn you're going to do for this calculation. First, you're going to compute the energy of each photon. That's a good way to start these problems. Next, how much energy is given to the cell every second? How many photons does that correspond to? How many electrons are produced? What is the charge of those electrons? What is the current that's produced? What is the resulting output power? And next, what is the efficiency? Those are the steps that you're going to do. Now, if you can do this problem and you can do these steps, you have mastered not just the details of the quantum physics that we're talking about, but also you've shown you've mastered the stuff we've talked about previously. So I want you to think about how you do this. I want you to pause. I want you to start these calculations. I want you to work your way through 1 through 8 of these steps. Go ahead and pause. Start working your way through. And we'll be back. Now, before we talk about the answers, I want to talk about some of the steps. What is the energy in joules of each photon? What I would do is I would just say, I'm going to compute the energy as 1240 divided by the wavelength. And if I do that, I get an energy in electron volts. And I can take that and I convert it to joules. So I'll take that energy and convert it to joules. What is the energy in joules delivered to the cell each second? Well, 1 watt of light falls on the cell. 1 watt is 1 joule per second. So in 1 second, how much energy falls on the cell? 1 joule. Then you have to figure out how many photons give rise to electrons each second. Okay, now let's think about this. We got 1 joule hitting every second, and each photon has a certain energy, so I can figure out the number of photons that are hitting the cell each second. And 50% of them give their energy to charge carriers. That is 50% of them free electrons. So you calculate the number of photons. Having calculated the number of photons, you can figure out how many electrons are produced every second. It's just 1/2 the number of photons. Each electron has a charge of E on it, okay, and that's 1.6 times 10 to the negative 19th coulombs. So I know the number of electrons every second. Each one of them has this much charge. So in 1 second, I have the number of electrons times the charge per electron. That's how much charge flows every second. And charge every second is current in amps. Now, if I know that, I know the current in amps, and I know the voltage, which is 0.5 volts, I can figure out the output power, because remember, the output power is just equal to I times delta V. So given that, I can compute the output power. I know how much energy is coming in. How much energy is coming in is 1 watt. I can calculate how much energy is going out, and I can take the output divided by the input, and I can use that to calculate an efficiency. So go back, fill in the missing pieces in this calculation, and I think it's worthwhile to take the time to get this one right, seriously. And so if you're struggling with this, we have class sessions on Piazza. Get on, type in your questions, help us help you work your way through this problem. This is something I felt was important enough for you folks to know how to do, that I work through this calculation. Make sure you know how to do each step. Make sure you know what assumptions are being made. Finish that calculation, and then we'll look at the answers. And these are the numbers that I get. The energy in joules of each photon, 3.3 times 10 to the negative 19th joules. So if I have 1 joule of light, 1 joule of photons, that means I have this many, I have double that many photons. Half of them give rise to electrons. And so I get this many electrons each second. That corresponds to this charge, this current, this power, and this efficiency. Step that calculation through. And if you have questions about any of it, get on Piazza when we are there and ask us about it. If you're doing this at a time when we're not on Piazza, go ahead and wait, or go ahead and put something in the class discussions. That's another way to get feedback. You are not doing this alone. Our instruction is remote, but not isolated. You are in contact with people who can help you through this. Go ahead and work your way through. Ask for some help. Make sure you know how to get to this final step before you go on. Now here's a question for you. If a solar cell is converting red light to electricity, it's more efficient than when it's converting blue light to efficiency. Why would that be true? I want you to think about this, and it's related to the problem that we just solved. So give that some thought. Think about what you just did. Think about how it relates to this question. Take a moment, think about it, and then we'll discuss it as a class. And of course, the key piece is this. If I have a solar cell and I have light comes in and hits the solar cell and it pops electrons off, it makes electrons kind of like go through a circuit, the electrons leave with a certain energy. And we saw in the last slide, the terminal voltage was 0.5 volts, okay? So that corresponds to an energy of 0.5 electron volts. Well, the photon that comes in has whatever energy it does. And if I have blue light, that's more energy per photon. If I have red light, I have less. Blue light, you might have an energy of 3 electron volts. So 3 electron volts in gives you 0.5 electron volts out. 1/6 of the energy is used. If I have red light, that corresponds to an energy of 2 electron volts. 2 electron volts in gives me 0.5 electron volts out. 1/4 of my energy is used. And so I get more efficiency see, for lower photon energy. So that's kind of an important part. And if you look at the response, like the amount of amps that you get per watt of incident light for real solar cells, you get more amps per watt for the longer wavelengths. That is absolutely true. And so if you want to make solar cells that are more efficient, one of the things they do is they make multi-layer cells, and multi-layer cells use the different wavelengths more efficiently. So one layer uses just the blue, and then one uses the green, and one uses the red. And if you do that, multi-layer or a multi-gap solar cell, you can get more energy, and that is mission critical, learning how to do this. But turns out plants already do this. Plants have a multi-gap system where they're going to use the blue light effectively and they're going to use the red light effectively. The only thing, ironically, they don't use is the stuff in the middle. They don't use the green, but they've got this multi-gap system, and so you actually get much more photosynthetic efficiency because you could effectively use those two ends of the visible light spectrum. And so words have known for a long time. Now, I want to talk briefly about the MRI, which is something that we talked about previously. And remember, we said compasses line up with fields. And so that if I have a compass that lines up with a field. Now, I want to take a look at this problem having to do with spins lining up in magnetic fields. And we saw, but if I have a quantum compass, like and considering an electron inside an atom, or a proton in a hydrogen atom in a magnetic field, a proton in a hydrogen atom in a magnetic field can only be lined up exactly with the field or exactly opposite the field. And it's got different energies, and it's really got two possible energy states. And we saw this previously. The proton can be in the state where it's lined up with the field, or it can be in the state where it's lined up opposite the field. It can be in one of those states or the other. It can't be in between. And so we've got a quantum system where if I want to make a proton go from the lower energy state to the higher energy state, I have to bring in a photon of a certain energy, and I can pop the photon from the lower energy state to the upper energy state. The energies of the states are mu times b. For the lower energy state, it's negative mu times b. For the positive energy state, it's positive mu times b. So we can calculate what is the photon energy corresponding to a spin flip. And the energy corresponding to that transition is 2 times mu times b. And we can calculate a frequency that corresponds to, and we can think about what type of electromagnetic wave that is. I want you to pause. I want you to calculate what is the energy corresponding to the spin flip. For that energy, what is the frequency, and what part of the electromagnetic spectrum is it? So this is something we talked about previously, but now we're looking at it as an example of a quantum system where I apply a photon and I pop a particle, in this case a proton, from a low energy state into a higher energy state. I want you to complete that calculation, and when you're done, come on back. Oh, and I'm going to pause for a minute because my wife is at the door, and I'm going to go ahead and let her in. So my wife Carol has just come in here. I'm going to ask her to say hi.
Hello, hi.
And Milo is here too. Milo's not saying hi. He's not such a vocal dog. Milo, speak. No, he's wagging his tail. He's really happy to see you all. He's happy to be here, but he's not gonna show that in any tangible way. But where were we? Oh yes, we were talking about energy levels of protons in magnetic fields. So I want you to calculate what energy corresponds to a spin flip of the proton in a 1 Tesla magnetic field. What frequency does that correspond to, and what type of electromagnetic wave is this? I want you to go ahead and complete that calculation, and we'll be back. Now, if you calculate the photon energy, that's just 2 times mu times b. That's the amount of energy from the lower energy state to the upper energy state. That's 2.8 times 10 to the negative 26 joules. Then I can figure out what frequency that corresponds to. It's a frequency of a photon. And remember, the energy of a photon is equal to Planck's constant times the frequency. And since I'm given an energy in joules, I'm going to choose the value of Planck's constant in joules times seconds. And to compute a frequency, when I do that, I get a frequency of 43 megahertz. That's in the radio frequency end of the spectrum. So the way that an MRI works is they pop the spins from the lower energy state into the upper energy state, and you can see inside a tube. And they have coils. One applies a really, really strong field. One is it makes the field change from place to place. And then the third, they have a radio frequency coil that emits frequencies in the radio frequency region of the spectrum. And those ones are the ones, how much absorption is there? If there's a lot of absorption, there's a lot of particles. And they change the field at different places in your body, so there is only one place on your body due to the gradient coils that has exactly the field necessary to have exactly the splitting between the energy states that will correspond to a spin flip. And so they basically change the field so that it has the right value of magnetic field at one spot in your body, and then they probe it and say how many molecules are there based on how much absorption of the RF do we have. That's how you make MRI images. Question: suppose I increase the field from 1 Tesla to 2 Teslas. How would that change the frequency of the wave necessary to cause the spin flip? I want you to think about the calculation that we just did and see how would it be changed if I made that change. Think about this, do a quick calculation, then we'll talk as a class. Well, if I've increased the field from 1 Tesla to 2 Tesla, I've increased the values of the energies because the energy levels are mu times B. So if B has gone up, the energies have gone up. So this energy goes up, this one is a bigger number, it's negative, and so it's a smaller energy. And so the difference between the two states is bigger. As a consequence, there's more energy required to pop a proton from the lower energy state to the upper energy state. Higher energy photon means higher frequency photon. So if I take the field and increase it from 1 Tesla to 2 Teslas, that's going to increase the frequency. Okay, as we saw. Now, we've seen that if you take particles and you constrain them to a certain place, that quantizes the energy levels, and we can only have certain possible transitions. Okay, and we've seen this for like the particle in a box system. One of the things corresponds to more closely spaced energy levels, which means smaller energies for transitions. And so I'm going to have a bit of atoms. But I want to think about this. This done on the homework assignment was this question. Okay, the molecules in rods and cones are tuned to absorb photons at particular energies. And the molecule, the retinol molecule, is basically a long chain molecule, and the electrons freely move along the chain reflected at the ends. This looks like the particle in a one-dimensional box, just like the dye molecules that we saw. Here's a question. The molecules in a red cone, which are tuned to absorb red light, compare those to the molecules in a blue cone, which are tuned to absorb blue light. Which has the longer box? And I want you to think about that in terms of what we've talked about. You had a chance to take a look at that on the homework assignment. Of course, if I have a bigger box for the red light than for the blue light. And that's how I get these 3 color cones that you have for your visions. I've got the blue, and I've got the green, and I've got the red. I've got slightly different molecules that are tuned to certain photon energies. And you can see there's kind of a broad peak for the red and the green and the blue. It's not just a precisely defined wavelength. There is a range of wavelengths that will correspond to absorption because the ends of the box are kind of fuzzy. It's not like a hard stop. It's kind of a fuzzy end to the box. Now, here's a question. I want to think about rod cells. Okay, and the rod cells in your eye, and those are the ones that are much more sensitive, and they're also more sensitive to motion. But the individual rod cells, they use this pigment called rhodopsin, and that particular pigment has a minimum photon energy of 1.9 electron volts. There's a threshold. Energy is lower than that, no transition. So what is the longest wavelength that a rod cell could detect? I want you to do a quick calculation, and then we'll talk as a class. Well, that calculation just uses our classic calculation, the wavelength. We want to know the longest wavelength. The energy of a photon is equal to 1240 divided by the wavelength, or the wavelength is equal to 1240 divided by the energy. I'm given the energy in electron volts. I can calculate the wavelength by your rod cells. And the rod cells don't respond to red light. It corresponds to a wavelength of 600 nanometers. That's in the red region of the spectrum. Mostly this. So that's why astronomers use red flashlights. They want to keep their night vision, and the night vision is astronomers use red flashlights, and if the wavelength of the red flashlight is greater than 650 nanometers, your cone cells pick it up. The rod cells don't, and the rod cells stay sensitive. They're not sensing any light, and so you keep your night vision. Now, it's also true that since you don't see red light with your rod cells, and your rod cells are the ones that are responsible for your night vision and also sensitive to motion, we don't paint fire engines red anymore. Fire engines aren't red because you're not very good at seeing red colors at night. And so now they're painted a color which corresponds to maximum sensitivity of your rod cells. And that just makes it easier to see the fire truck when it's coming. Now, I want to talk about molecules, and we've talked about the fact that if you have electrons, you can pop them from a lower energy state up to a higher energy state. But if you have a molecule, instead of having just single possible levels, if you go to a molecule, you have bands of states. You can have a whole bunch of different states, but they're packed in really, really tightly. And this is talked about in chapter 29. So instead of just having single lines, I end up having bands. And so as a consequence, I get a range of possible photon energies. For single atoms, I just get, you pop it from the lower energy state to the upper energy state, from the upper to the lower. There's a very defined energy. But for molecules, I have these bands. And so as a consequence, I can have a range of energies for absorption and a range of energies for emission, because I can go from the bottom of this energy band anywhere inside this one, and I can go from the bottom of this one anywhere inside this one. So I get a range of energies that are absorbed and a range of energies that are emitted. And if you look at the picture that I've drawn here, and this is typically what's going to happen, the electrons are going to be chilling in the lower part of this energy band here. And so I can pop them up into to anywhere in this upper band. They're also then they're going to chill in the lower part of this upper band, and they're going to fall anywhere in the lower band. But if you look at the lengths of the arrows for this emission of photons, it's a lower energy transition than for the absorption of the photons. And that is occasionally, as often the case. And if we look at the situation of fluorescence, there's a range of wavelengths that can excite electrons to the upper band. Then there's some sort of internal transition where they fall to the lower end of the upper band. And then when they fall back to the lower band, they emit photons. The wavelengths they emit are longer than the wavelengths that are absorbed. So in one case that is dealt with fluorescence, there's a little video. You will see in a video, which I want you to take a look at, and see situations where the absorption and the emission are different wavelengths and band structure, and how you have different energies for the energy state, and then they'll drop into the lower. Okay, there's a video that's made that deals with fluorescence, this phenomenon of fluorescence. And so I forgot to put the little video here, but I want you to take a look at one of my key concept videos. And it's the concept of fluorescence. And so go ahead and pause and take a look at the key concept video for fluorescence, and it talks about the emission and for the absorption, and that makes fluorescence. Related to that, also up into that energy state and explored in the video, is the concept of phosphorescence, which is things that glow in the dark. But you can also raise the energies to the electrons, to the up those electrons, can produce a state by doing things chemically, and that's how creatures that have bioluminescence make it happen. And in the video, I explore a related concept of chemoluminescence. And you can use chemistry basically to produce light, or you can use biology to produce light, but you basically light that way. And that brings us to an end of what we want to say about quantum mechanics. But before I do that, I want to give you a home experiment you can try. I want you to go get wintergreen lifesavers. Okay? I want you to get wintergreen lifesavers. And you're going to have to get somebody that you trust and you can get close to. So get some wintergreen lifesavers, go into a really, really dark space, let your eyes get dark adapted. You can do this in a closet, you can do it in a basement, get someplace really, really dark, and then take that wintergreen lifesaver and crunch it really hard between your teeth. And when you do that, you will see a flash of light. And the reason is this: when the sugar crystals in the lifesavers are crushed, triboelectricity makes it create a spark. The spark ionizes nitrogen molecules that emits ultraviolet light. The ultraviolet light excites the methyl salicylate, which is the wintergreen flavor, and it causes it to fluoresce. So it's a multiple stage quantum phenomenon. When I was a kid, we used to call this sparking, and you would take someone that you were, maybe this was a middle school thing, take someone you had a crush on and you would invite them to go into a dark place and crunch wintergreen lifesavers between your teeth with. So it's kind of a junior high school thing. Anyway, it's kind of a thing, and it's awesome. Go get some wintergreen lifesavers. Go to a dark place with someone that you're not going to catch the virus from, and try some sparking. And that is our closing thing for quantum mechanics, except for one other thing that we show in the video, which I've posted on Fluorescence, and that's this. If you take Vaseline glass, that's a particular kind of glass, and you put it on a deck where it emits fluorescent light, emits ultraviolet light, the glass fluoresces. And this glass fluoresces really, really strongly, but in addition to being fluorescent, it is also radioactive. Why would you make glassware which is radioactive? That's kind of an amazing question, and it's one that we'll talk about next week when we talk about nuclear physics. Thank you very much for joining me, and I look forward to talking with you next week.